Hello everybody. So this is my part 2 of my lecture 2 on basic definitions and relationships. As we can recall, in part 1 of this lecture, we have studied about the different basic terminologies and definitions and relationships between different physical properties of soil. Right. So we know that and we have also talked about that in order to assess the engineering performance and the behavior of a soil, it is important to evaluate all the fundamental properties that we have talked about. So, while some of the properties like the water content, the specific gravity, the unit weight of the soil, they can be easily determined from the laboratory tests. So, we will talk about few tests as we go ahead in this series. While we can see some other properties like the void ratio, the unit weight of the solids, the saturation of the sample cannot be easily determined from laboratory tests, right? Or I mean to say, they cannot be evaluated directly. However, all these properties also interdependent. So what we have done, we have tried to obtain various mathematical relationships between two or more such properties. Thus, suppose for some properties, when we can directly determine them, the other properties through these mathematical relationships, they can be indirectly determined with respect to the known properties. So, the functional relationships have a very important role to play in this soil mechanics. So now in this lecture we will see that relationships, how the definition of the fundamental physical properties that we have talked about will be useful in solving various problems or determining various properties with the help of certain example problems. So this is our first example problem. As we can see on the screen, let me read out for the viewers. So a soil sample has a porosity of 44% and a moisture content of 10%. The specific gravity is 2.72. So we have to find out the dry unit weight of the sample, the moist unit weight of the sample, and how much water we have to add to the sample to make it fully saturated, right? So from the first part 1 of this lecture 2, we can recall the relationship we have find out to find the unit weight of the sample. So the unit weight is equal to G plus SE, 1 plus E into unit weight of water, right? So from it we have what further deduced, like for dry unit weight of the sample, the saturation is equal to 0, right? So the relationship reduces to dry unit weight G into gamma W 1 plus E, right? So from this relationship we know what is the unit weight of water, that is the standard which we take as 9.81 kilonewton per meter cube. We have already the specific gravity given 2.72, and we need to know the void ratio which is not given. So what we can do, we can again recall a relationship that we have obtained between porosity of the sample and the void ratio of the sample, as the porosity of the sample is given. So let us find out void ratio is equal to N1 minus N. I hope we can recall it, and putting N is 44%, that means 0.44, 1 minus 0.44, we get the void ratio as 0.786, right? So we just simply put the value of void ratio here. So the specific gravity is 2.72. We have the unit weight of water 9.81, and we have 1 plus 0.786. So we can take out our calculators and calculate it. So what we get the dry unit weight as 14.94 kilonewton per meter cube. So this is my answer to the dry unit weight of the sample. So let us now calculate what is the moist unit weight of the sample. So similarly, from this relationship we can find out. So moist unit weight means the soil is partially saturated, right? The soil has some saturation content. However, we do not know what is the saturation content of the sample, but we do know the water content of the sample, the porosity and the specific gravity. So however, thus we can try to just write this SC in terms of probably this water content. So again, recalling the relationships, we can write omega G is equal to SE, right? So we simply put SC as omega G in the relation, suppose 1, right? So we get gamma is equal to G plus Wg divided by 1 plus E as it is given into unit weight of water. So W is the water content of the sample. We have already know in this, which is 10%. So G we have given 2.72. Water content is 10%, that is 0.10 into 2.72 divided by 1 plus 0.786, which is my void ratio, and unit weight of water is 9.81. So from this we get the value of unit weight or moist unit weight as 16.43 kilonewton per meter cube, right? Now we need to find out what is my water to add to the sample which will make it fully saturated, right? So fully saturated, what we do, let us find out what is now gamma saturated, right? So gamma saturated, we know we have is G plus SC 1 plus E, gamma water, unit weight of water. So S is here 1 or 100%, right? So G we substitute as 2.72, which is already given. S is 1. Void ratio we have found at 0.786, and in the denominator is 1 plus 0.786, and we know the unit weight of water as 9.81. So from it we get the value as 19.26 kilonewton per meter cube. So why did we find out the gamma saturated? So we know that the unit weight of the sample is weight by volume, right? Weight of the sample by volume. So here the volume of the sample is fixed. In the weight, we know the weight is equal to the weight of the solids plus the weight of the water, right? So weight of the solids is also fixed, be it whatever saturation content we have, right? So whether it's a dry soil or it's a saturated soil, the weight of solids is fixed. So the difference would be in the weight of the water in the voids, right? So if we just simply subtract the gamma saturated minus the gamma moist that we have found out, so simply we can get what will be the weight of the water to be added to the soil sample per unit volume, right? So we know the saturation unit weight we have get is 19.26. We found out what is the moist unit weight already in the part 2 of this question, which is 16.43, right? So if we subtract, we get the value is 2.83 kilonewton per meter cube, right? So this is my weight of the water to be added per meter cube of the volume of the sample. So this is a very simple question with the various relationships between gamma, that's the unit weight, with specific gravity and saturation and void ratio. And we also substituted when found the relationship between water content and saturation and void ratio. We also showed how we use the relationship between porosity and void ratio. So through these various relationships, we can find out one property with reference to the other property. So this is my example 2. We'll solve this problem. Let me read out. An embankment was constructed with clay soil at a water content of 10%. The degree of saturation of the sample was reported as 55% after construction. During monsoon, the soil absorbed water and its degree of saturation increased to 85%. So, determine the water content at this stage. Also find out the saturation of the sample when the water content reaches 5% in dry season. So let us start solving it. So what is our given, right? So given is our water content W, it's equal to 10%, and the of saturation is equal to 55% at this stage after construction. So from this, let us find out what is the void ratio of the sample. Okay, so let's recall the relationship Wg equal to Se. Here we are not given the G of the sample, so let us consider the G of the sample is suppose 2.68, that is the specific gravity of the solids is 2.68. Okay, so we just put the values. Water content is 10%, G is 2.68, the saturation comes in the denominator, it's 55%, and can get the void ratio of the sample. So if we work it out, we get the void ratio as 0.487. Okay, so now what happened during monsoon? The soil has absorbed water, degree of saturation has increased to 85%. So what does that mean? So it means that the saturation has increased, but my void ratio has remained the same. Why this is so? We can definition of void ratio is volume of voids to the volume of solids. So we know the volume of solids of a soil always remains the same, right? And when the saturation has increased, that means the water content in the voids has increased, but there is no change in the volume of voids, right? So simply the water has entered, that is during monsoon, you suppose during rainfall, the water has entered into the voids of the sample by replacing the air in the voids. So the total volume of the voids remains the same, and as a result the void ratio remains the same. So again, in my next case, suppose we again write the relationship of Wg equal to Se. So we know we have to determine the water content after the saturation has increased, right? So our water content in this stage is unknown. The specific gravity of the solids remains the same, right? It's 2.8. The saturation has increased to 85%, so now it's 0.85. And the void ratio, as I talked about, remains the same, so it's 0.487, right? So if we work this out, my water content will come as 0.15, or more specifically we can write it at 15.4%. Water content we express as percentage, right? So my second part is also calculated. This is my first part only. E was just it, so that it will help in calculation this water content. So my next part is that we have to find out the saturation of the soil, right? So saturation of the soil when the water content reduces to 5%. So similarly my E remains the same. Now again, using the same relationship, we can write my water content reduces to 5%, so it is 0.05. My G remains the same, it's 2.68. and we have to find out the saturation, so it is unknown in this case, and ratio remains the same like before, is 0.487. so if we calculate this, my saturation comes as 0.275, or we can write it as 27.5%. We also express saturation of the soil in percentage. So I have got my two answer. The water content of the sample is 15.4%. After it the saturation increased to 85%, and finally in the dry season my saturation of the sample 27.5%. so this is my two answers. So this is our next problem. Let us try to solve this. So a 12.6 centimeter in height and 10.2 centimeter in diameter core cutter, which weighs of 0.070 gram, was used to find the in situ unit weight of an embankment. It was noted that the weight of the core cutter filled with soil was 2970 gram. The water content of the sample is 8% and the specific gravity is 2.69. So we have to find the in situ dry unit weight and the porosity of the sample. Again, due to rains, the embankment becomes fully saturated. Find the increase in the water content and the bulk unit weight considering no volume change in sample on saturation. So a core cutter is used to determine the in situ weight of the soil. We will learn about it later. So for now, let us try to solve it. So let me write the height of it as h is given 12.6 centimeter. The diameter, let us represent by d, is given as 10.2 centimeter, right? So we know the height and the diameter. The core cutter is a cylindrical apparatus, or it's a cylinder basically, metallic cylinder. So we try to say that the soil inside the core cutter, that is the volume of the core cutter, gives the volume of the soil sample. So we determine the volume as pi by 4 d square h, right? So it's pi by 4 into 10.2 whole square into 12.6. So by solving it, we get it's equal to 1029.7 centimeter cube. It's a volume of the soil sample, right? Now the mass of the core cutter is 1070 gram, right? Or the mass of core cutter plus soil is given, that is the core cutter filled with soil, it is 2970 gram. So what is my mass of soil? Simply, suppose this is 1 and this is 2, so simply 1 minus 2, right? So if we subtract this, we get is 1900 gram, right? So we have got the mass of the sample as 1900 gram. Now let us find out the density of the sample, right? So our density is therefore mass by, right? So mass we have got as 1900. The volume of our sample is the volume of the core cutter is 1029.7, and therefore we get as 1.84 gram per cc. So we are asked to find out the unit weight. So to convert density into unit weight, what we do? We simply multiply by 9.81. So we get 18.1 kilonewton per meter cube. Now already given, my water content of the sample is 8% and my specific gravity of the soil sample is 2.69. Okay, so let us find out what is my dry unit weight of the sample, right? So we have to find out my dry unit weight, which is gamma D. Let's recall the relationship between dry unit weight and unit weight of the sample through the water content of the, right? So unit weight we have already found out is 18.1 divided by 1 plus water content of the sample is 8%, so 0.08, right? So my answer comes as 16.7 kilonewton per meter cube, right? Now we have been asked to find out the porosity of the sample. So to find out the porosity, we can first determine what is the void ratio of the sample. So if you know the void ratio of the sample, simply by the relation void ratio and porosity, we can find the porosity. So void ratio and unit weight relationship we know, and therefore we are finding the void ratio first because we are more easy in that relationship. So we know the gamma D, it's equal to G unit weight of water divided by 1 plus E. So I hope we all recall this relation. So we simply know what is the value of gamma D, which is 16.76. Simply substitute the values. G we already know is 2.6. Unit weight is 9.81 divided by 1 plus E. So we simply make it a subject of formula and we find out E as 0.574. So we know the relationship between E and N. Therefore, void porosity of the sample, it's equal to E by 1 plus C. Simply we substitute E here and we get the porosity of the sample as 0.365, or we can percentage is 36.5%, right? So we have got the porosity, we have got the dry unit weight of the soil sample. So now our next part of the question is that due to rains our embankment becomes fully saturated, and we have to find out the increase in water content of the sample and the increase in the bulk unit weight of the sample, right? So we know that we did a similar problem in the previous example, like when the saturation of the soil increases, the void ratio however remains the same, right? Because it's the same volume of voids where the water is entering, simply replacing the air, right? So we can use the relationship like we have used in the previous example, like Wg is equal to Se. So this we are trying to solve the third part of the question, is equal to S E. Okay, so the due to rains the soil is fully saturated now, so S is equal to 1 or 100%, right? So here my specific gravity remains the same, which is 2.69. my saturation has 1 or 100%, and my void ratio also remains the same, right, that we have calculated as 0.574 in the part 2 of the question, right. So simply our water content now becomes S is 1, E is 0.574, and the gravity remains the same, it's 2.69. So if we calculate this, we will get as water content is equal to 0.213, or we can express as percentage is 21.3%. Okay, so what is my increase in the water content due to? So my previous water content was already given as 8%, so now the new is 21.3%. So 21.3 minus 8, so we get it as an increase water content by 13.3%. Now we have to find out what is the increase in the bulk unit weight of the sample. So the previous unit weight of the samples was 18.1 kilonewton per meter cube after construction. Now to find out the saturated unit weight of the sample, we can simply use the relationship of gamma D, it's equal to gamma 1 plus water content of the sample. So this gamma is now saturated, right? So as the oil has become saturated due to the rains, and the water content is a new water content that we have get it, right? So this is my new water content. So we know the dry unit weight of the sample we have calculated in part 1 of the sample. So we get my saturated unit weight, it's equal to dry unit weight, which is my have come 16.76 into 1 plus water content of the sample, it's 21p, so it's 0.213, and we get the saturated unit weight as 20.33 kilonewton per meter cube, right. So my previous unit weight of the soil of the embankment was 18.1, and now after rains it has become 20.33. So what is my increase in water content? Sorry, what is my increase in the unit weight? So it's equal to 20.33 minus my 18.1, right. So this is comes to 2.23 kilonewton per meter cube. Okay, so now what we would do, we have solved this by using the formulas and the relationships that we have learnt about previously. But if we can recall, in the part 1 of the lecture, we have also talked about the phase diagram, right? So what we can do, we will see that these problems can similarly, by recalling the relationships as we solve it, by using the phase diagram and find out the volumetric and the gravimetric composition of the different soil solids and water and air, and write it appropriate in the block diagram or the phase diagram. Using that, we can also solve the same problem, as it will be helpful in giving a diagrammatic view to see how it is getting solved. Okay, so we will solve the same problem once again, but now using the phase diagram. So we draw our method 2, we are trying to solve the same problem by method 2 using phase diagram. So this is my phase diagram of a partially saturated soil. So this is my soil solids, this is my water, and this is my air. Okay, so we will write the aggregate mass and volume of the different phases of the soil in this diagram. Okay, so let us start solving it. So we are given that our water of the sample is 8%, that is 0.8. So water content, we can recall the definition, is the mass of water by the mass of the solids. So we can make some mathematical changes to find out, so where we can bring the total mass sample here by simply, suppose we add 1 to the numerator, and similarly we in the right hand side we get mass of water by mass of the solid. So simple mathematics we are doing. So we get 1 plus weight of is the total mass of the sample by the mass of the solids, right? So my mass of the solids we can calculate, it's equal to the total mass of the sample. The total mass of the sample is given, which is my 1900 gram, that is the mass of the core cutter plus the mass of the empty core cutter, right? So my total mass is 1900 gram, we have already found out before, and this is my 1 plus water content, so 1 plus 0.8. Therefore what we get, my mass of the solids is 175 gram. So the viewers can calculate it with calculator and see what they are getting. So simply what we can do, we can write it here in the phase diagram. My mass of the solids is coming as 1759 gram. Okay, now let us calculate what is my mass of water. Mass of water is simply the total mass of the soil minus the mass of the solids. As we consider the mass of the air is negligible, that is 0. Therefore my mass of the water is 190 minus 1759 gram, which is coming as 141 gram. So let us write it here to 141 gram, right? So let us not unit because we've already written on the top of it. Okay, so now let us find out the respective volumes of the air, water and solids also. Therefore, suppose my density of water, we know it's equal to mass of water by volume of water, right? So all these definitions we have read in the part 1 of the lecture. Now we know the water, which is 141. We have to find out the volume of water. We know the density of water, which is standard. In here we are writing the CGS unit is 1 gram per cc, right? So basically now the volume of water becomes 141 divided by 1, that is 140 cc. So similarly we write it here, that is the volume of water is 141. Now what will be my volume of the solids, right? So before that we recall the what is G. So my specific gravity, it's equal to unit of the solids by unit weight of water. Why we have written this? Because this unit weight of the solids will be helpful to find out what is the volume of the solids. So we know that unit weight of the solids, or let me write it in form of density because we are in gram per cc. So it's rho S by rho W. So we can write the density of solids is equal to the mass of the solids by the volume of the solids. So we simply substitute rho S from here. So we get G, it's equal to mass of the solids, volume of the solids into rho W. Therefore my volume of the solids comes out as mass of the solids G rho W. My mass of the solids we already found out, that is 1759. So 1759 divided by the specific gravity we know 2.69, and rho W is 1 gram per cc. So let me calculate. So it is coming as 653. Okay, so 650.9 cc, it's my volume of the solids. So we can write it here 653.9, it's my volume of the solids. Now what is my volume of air? So we have already known what is my volume of the core cutter, which is equal to the volume of the total soil sample. So this was already calculated before. 1029.7 is my total volume of the sample. Therefore from it we can simply determine what is my volume of the voids, right? So my volume of the voids is 1029.7 minus the volume of the solids, that is 653.9. so we will get is 375.8 is the volume of my. Okay, so we have already give a in this phase diagram we give a diagrammatic view of the different volumetric and the gravimetric components of air, water and solids. So now we will solve what asked in the problem by seeing this diagram only. So we now have been asked to find out what is my dry unit weight of the sample and the porosity of the sample. So to obtain the dry unit weight, first find the bulk unit weight of the sample. So we know the bulk unit weight, or we can write, suppose first my unit density of the sample, that is not unit, the density of the sample is total mass of the soil by the volume of the soil, right? So total mass we can see in the previous slide, the phase diagram. The mass of the sample is 1900 gram and the total volume of the sample is 1029.7. so we get is 1.84 gram per cc. Now if we want to convert it into unit weight as asked, we just simply multiply it by 9.81 and we get 18.05 kilonewton per meter cube. We are asked to find the dry unit weight, so let us write in the form of unit weight. So dry unit weight is the unit weight of the sample gamma divided by 1 plus water content, right? Okay, no, we are not using formula, right? We are using the phase diagram, so we won't use this. Instead we just recall the basic definition and not the relation, that is gamma d, it's equal to the weight of the soil solids divided by the volume of the solids, right? Or sorry, the total volume of the sample. So weight of the solid, basically we have the mass of the solids given, right? So we have 1759 gram. Since we will find out in unit dry density or dry unit weight, let us already keep a 9.81 in multiplication so that we can obtain in terms of kilonewton per meter cube. So the weight of the solids divided by the volume, the total volume as the volume of the core cutter, as we have written in the phase diagram, is 1029.7. So we can obtain it as 1.78 gram per cc, or in kilonewton per meter cube we obtain it as 16.76 kilonewton per meter cube. Okay, so now we are having, this is my one answer that we have got to the phase diagram. Now the porosity, we know, recall the definition, it's volume of voids to the total volume. Refer to the phase diagram, we have already calculated the volume of voids, which is 375.8, and have the total volume is 1029.7. Therefore our void ratio is coming as 0.364, or more specifically 36.4%. okay, so now what's rain is happening, right? So due to rain, the soil becomes fully saturated, and now our three-phase system has been converted to a two-phase system, as the water has taken all the places of the air in the voids. So two-phase system, we have simply water and we have simply the soil solids, right? So we know that the volume of the solids and the weight of the solids remains the same. So from the previous phase diagram, we just simply write it. The weight of the solids is 1759 and the water solids is 653.9. so this is the volume in cc, this is the mass in gram, right? Now we can also, what is my weight of water, that's the mass of water. So simply we recall the density of water is equal to mass by volume, that is my mass of water by volume of water, right? So my mass of water we need to find out, right? While we know my volume of water, how do we know this? Because from the previous diagram we have already calculated what is my volume of the voids. So we know that the volume of the voids remains the same even if the soil gets heated, as simply the water takes the place of the voids. So this is my 375.8. so what is my mass of water? Simply my mass of water is rho W into volume of water. So rho W is 1 gram per cc, volume of is 375.8. So similarly my mass of the water also becomes 375.8. so we write it here, 375.8. Now we have been asked to find out that how much the water content has increased, right? So my new water content is water content by mass of water by mass of solids, right? So my mass of water is 375.8 and my mass of my solids, from the phase diagram we see it's 1759. We calculate this and we get it's 213, or simply that is becomes, or it's 21.3% to be more exact. So my water content previously was my 8% and now it's 21.3%. so increase is equal to 21.3 minus 8, which becomes 13.3, right? 13.3%. Now what is my increase in the unit weight of the sample, right? So increase in the unit weight, that is our gamma, or my density of the sample has increased due to the infiltrating water in the pores, right? So my gamma saturated is
weight of the soil by volume, and this weight is the weight of the saturated soil. Or we can, in terms of density, that is my rho saturated is equal to rho mass of the saturated soil divided by volume. Okay, let me erase this so it will give me space to do the further calculations. Please bear with me. Okay, so my mass of the sat soil is my total mass of the soil, right? So we can see from the phase diagram, my mass is equal to 375.8, which is my mass of the water, plus my mass of the solids is 1759, right, divided by my total volume. Similarly, my volume, see in the left hand side of the phase diagram, is 375.8 is the volume of water plus 653.9, right? So it becomes 2.07 gram per cc. This is my saturated density. If we want in the unit, saturated unit weight, we simply multiply by 9.81 and we get 20.33 kilonewton per meter cube. So what is my increase in the unit weight? So similarly, the volume of the sample remains the same. It's just, and the weight of the solids is also the same. It's the weight of the water that is increasing as saturation has increased. So my per meter cube of my soil sample, my increase in the weight of the water, or that is, we can say my increase in the bulk unit weight, is increase in bulk unit weight. It's equal to, we are simply subtracting from my previous weight that have come around 18.1, right, or 18.05 to be exact. So we are just subtracting 20.33 minus 18.05. So it's 20.33 minus 18.05. So it is coming at 2.28 kilonewton per meter cube. So it's 2.28 Newton per meter cube. So we have got our answers. So this is my increase in the moisture or the water content of the sample that we have been asked to find out, and this is my increase in the bulk unit weight of the sample we have been asked out, like after rain what is the increase, right? So this is it. So we have solved some few problems which has helped us to recall the different definitions of the fundamental properties, and we made use of the different relationships between the fundamental properties to find out some unknown properties. And also we saw in the last example that how we utilize the phase diagram in order to determine some of the properties. So I'll suggest for all the viewers that when I have solved this, you also solve it along with it, which will help you to understand it better. And also you can refer to different books on soil mechanics. Some of the references I've already shared in the part 1 of my lecture in the basic introduction of soil mechanics. So you can go through several example problems solved there. It will help you to recall and keep in your mind the definitions more, and be more used to the use of the relationships, and also understand the phase diagrams better. So what you can do, the problems which I've solved just using the relationships, you can also try solving them by the of using a phase diagram, so it will be more clear to all of you. So that's all for today's lecture. We will meet in the next lecture. where we will talk about the index properties of the soil. So thank you.